basic introduction to cosmology. I just want to remind you that where we were. So we derived Einstein's equation. We showed Einstein's equation. It can be derived from an action principle. And we started solving Einstein's equation for the very simple case of a universe that's homogeneous and isotropic. And that's what describes the average universe. We call the average universe. And in that case, the metric that describes the universe is this Friedmann-Lemaître-Robertson-Walker metric. And to solve Einstein's equation, we have the left-hand side, which is basically geometry. The right-hand side is from energy momentum tensor, so matter, energy, etc. And on the left-hand side, in order to solve Einstein's equation, we have to compute the Ricci tensor and the Ricci scalar. And this was the exercise I left for you to compute the Ricci tensor and the Ricci scalar in the simple case of Friedmann-Lemaître-Robertson-Walker metric. And we're going to use this later on to derive the equations that describe the evolution of the average universe. Then, before doing that, I decided to do a small tour with a small detour, actually, and to extra dimensions. And the reason I decided to do that, first of all, interesting, and second, it matters in more modern models for particle physics. So, as I said, the first lecture, when I started studying extra dimensions was not directly important for particle physics or for phenomenology, and now it becomes an essential part of model building for particle physics models. So this is just to give you a flavor of how geometry matters and how can you learn from geometry. I gave you this very simple example of the possibility of having flat extra dimensions, and then the Einstein-Hilbert tensor, Einstein-Hilbert action, I wrote it down here. We went through this yesterday. And in this very simple model where only gravity propagates in the extra dimensions, what happens in the end is that you can explain, quote unquote, the weakness of the gravitational interaction by a volume effect, a volume of extra dimensions. So this is the conclusion of this model of universal extra dimensions, flat extra dimensions. And then I just, for fun, I left it as an exercise to compute or to estimate the size of these extra dimensions. And given that the fundamental scale is 1 TeV of these extra dimensions, so that it's accessible to colliders and for different values of number of extra dimensions. This is so if you go to n, the number of extra dimensions larger than 2, basically there are no bounds from experiments and that test gravity at these very small scales. Now I want to talk a little bit about another model of extra dimensions, which has more appealing features for particle physics. And this is so-called the a model which has one extra dimension, but the extra dimension is not flat, warped. And this model was proposed by Lisa Randall and Raman Sundram in 1999. So last century physics again. And it has only one extra compact dimension, which we call y here. So this is a fifth dimension. And the idea is that each point in the fifth dimension, you have a four-dimensional brane, if you want, surface. It's a four-dimensional Minkowski vector. So the metric for this particular model can be written as this, as follows. So you have the usual Minkowski metric here, but multiplied by a factor which depends on the extra dimension. So each point in extra dimension, you have a flat Minkowski space-time, but the scales are different because they're affected by the position in this fifth dimension. the factor A of y here that describes this effect of changing the four-dimensional space in the fifth dimensional direction is called the warp factor. And let's say, for the sake of the argument, that this is a compact extra dimension, so y, this extra dimension y, goes from 0 to L. Then you can consider the rotational action, the bulk cosmological constant, which we call lambda 5 here. So this is the Ricci scalar in 5 dimensions with that metric. And this is another energy scale, K star. And G5 is the determinant of the 5-dimensional metric. So you can use this action, again, to find Einstein's equations. Einstein's equation is just, again, Ricci tensor minus 1/2 metric Ricci scalar equals K squared. This energy scale here actually has dimensions. If you go through the exercise, it has dimensions of K star square has dimensions of e to the minus 3 and times lambda 5. So this 5-dimensional logical constant times the metric again. So this is interesting. So what I want to show you, okay, so can you solve Einstein's equation in this case? And what are the consequences? And in fact, you can solve these equations. You have to compute the Ricci. The only thing I have to do is to compute the Ricci tensor and the Ricci scalar in this metric. And if you write the 5-5 component of Einstein's equation, this is the 5-5 component of Einstein tensor. Just remind you that Einstein tensor is just this combination here, which is called G, Mn. So Mn is because you're one extra dimension. And Einstein's equation is just given by this, G55 equals minus K star squared times the cosmological constant in 5 dimensions times the 5-5 component of the metric. Now, the question is, how do you compute G55? And probably, if you try to do the exercise that I gave you here, it's a mechanical thing to compute the, given a metric, it's just some steps that you have to follow in order to compute the Ricci tensor and the Ricci scalar. But you have to do this once this exercise to learn how to do it. But in principle, this can be automated. So there are the codes where you can give the metric and it spits out the Einstein tensor if you want. So I tried the different codes, and there was one that was just turned public a couple of weeks ago called Einstein Pi. So it's a Python program that can compute some, actually can solve some Einstein's equations numerically. And there's also something called Maxima. So I tried those, and I didn't have any success. I tried those because they're free, and I wanted to do this with free software. But if you guys can find a software that works in things in a metric, please let me know, because I couldn't find it. So I decided to use a package for Mathematica, which is called GR. And in GR, this package, you just give the components of the metric. So this is the covariant metric tensor. So this is the metric I just wrote in here, this one here. I just put it in this package. So instead of y, I'm using u here for no particular reason. And here, if you give the metric, it can give you everything. Particularly, it gives you the 5-5 component of the Einstein, of the covariant Einstein tensor. So sorry, this is G55 here. And this is the result. So you can go through the algebra, the exercise. I was a bit lazy, so I used this package. And so just to show you that G55 is 6 times a prime of u squared. So this derivative here is with respect to this extra dimension. So you can solve Einstein's equation because you also have G55. And if I call, so the equation is this, a prime of y is kappa, where kappa is just k squared k star squared lambda 5 divided by 6. The 6 comes from this factor 6 here. So we can solve this, and the solution is that this factor, warp factor, goes linearly with the extra dimension 1. It means that in the metric, the metric changes exponentially, right? So the metric changes exponentially in each slice of this fifth dimension. This is what we call warped factors. And again, this is the idea behind these models, that you have different branes at locations at 0, for instance, and at L in this extra dimension Y. And we live in one of these branes, and gravity is localized in the other brane. And that actually is an explanation of why the electroweak scale, so this why the electroweak scale is so much smaller than the Planck scale. So so warping in principle solves what is called the hierarchy problem that you hear more next week, without large numbers, so without fine-tuning. And in fact, if say the electroweak, our world, the electroweak world, is one side of the brane, where L equals 30, for instance, and the Planck scale, the gravity is in the other side of the brane, you can show that there's this relation here. And if you choose that k times L, so L is the size of extra dimension, is of order 30, for instance, and this can solve the hierarchy problem. So this model, Reynolds-Sundar model, they were or type of class of models, they were proposed in order to tackle this issue of hierarchy. Also, in this type of models, again, new particles are predicted, and there are some things called Kaluza-Klein excitations or resonances. And I'm sure that next week we have much more about this in Chaco's lectures on beyond standard model physics. I just wanted to show that geometry can play a role in particle physics, which is something I was not familiar when I was a student. So this ends this interlude, and for the rest of the lectures, we'll be back to 4 dimensions, and now I stop for questions.
There is a question by Arpon Paul, who asks, how do we relate the 4D cosmological constant with the 5D cosmological constant?
Yeah. So the 5D cosmological constant lives in this bulk here. So you actually have to introduce things also on the branes that can resemble cosmological constants. So those are boundary conditions that you have to impose in this type of metric. So it's not in principle, it's not even related. The 5-dimensional cosmological constant is related to some the 4-dimensional boundary. 4-dimensional cosmological constant is some boundary conditions you have to impose in this type of models. Any more questions, João?
No, there are no more questions.
Yeah. Again, this was very superficial. My intention was just to show how you can solve Einstein's equation in more complex geometries, and how these more complex geometries are motivated by particle physics problems. Okay, and these are, as I said before, these extra dimensions, they became a very important tool in the construction of theories beyond the standard model. This was my only goal. This very simple and deep work. Okay. So now we go back, and of course, cosmology changes, everything changes when I have extra dimensions, not the main issue. So I want to go back to 4 dimensions and go back to the very, very standard cosmology for the rest of this course. Okay, so we talked about the left-hand side of Einstein's equation. Again, the Einstein tensor, if you want, which is determined by the metric. And now I want to talk a little bit more on about the right-hand side of Einstein's equation. So the right-hand side of Einstein's equation has to do with the energy momentum tensor and the contributions of matter and energy to the energy momentum tensor. So usually we assume that we can describe the components of the universe as what people call perfect fluids. And this is true when the universe has this approximation of being homogeneous and isotropic. So at every point in this medium in the universe, there's a locally inertial frame, which we call the rest frame, in which the fluid is homogeneous and isotropic. So this is consistent with the assumption of Freeman-Matthew-Robertson-Walker metric. And therefore, we parameterize this energy momentum tensor of this fluid by its density. So the 0,0 component is a density, energy density of this fluid. And the spatial components relate to pressure. And then you have some zero I components, which are zero because of isotropy. So the homogeneity assumption also tells you that both the density and the pressure, they are space independent, because the universe is the same in every point that you look at, but can depend on time. So as the universe evolves, and the density and the pressure can change the whole universe. So we can write the energy momentum tensor rest frame as this matrix representation here, and indices are important. And just to tell you that if you're not in the rest frame, but you're in a frame with a given 4 velocity, you can write the energy momentum tensor in this way using the 4 velocities here. And of course, this is also when you include perturbations, this whole description changes, and you have to include the anisotropic stress, dissipation, etc. But for the moment, we're talking about the average universe. So this is going to be our energy momentum tensor. So again, we are thinking about a fluid description of the matter and energy components of the universe. And now we are ready to solve Einstein's equation for the average universe. And solving the Einstein's equation will give you what's called Friedmann's equation. Alexander Friedmann was the first person to solve Einstein's equation in this very simple framework in the 1920s. And he actually found that the universe was expanding, which led Einstein very angry. That's another one. So the 0,0 component of Einstein's equation, just Ricci 0,0 minus a half of metric 0,0 times Ricci scalar equals 8 pi g. G is the Newton constant T00. T00 is rho, and if you plug in the values that you obtain for the 0,0 component of the Ricci tensor and the Ricci scalar, this is the equation you're going to get. So this equation relates the expansion rate of the universe. So h dot over h is the expansion rate. You can write this as capital H squared. If you remember, that was the definition of the Hubble function. H dot over h squared is 8 pi g over 3 times the energy density of the fluid. So this is the 0,0 component of Einstein's equation. And this is going to be a very important equation that we're going to use throughout these lectures to understand how the average universe evolves. Now the II component, again, this is just the I'm just writing the II component of Einstein's equation. They're in principle 3 equations. They're all the same because the components in II is the same. And the equation can be written as this, again, plugging in the values that you obtain in the exercise. You can write this as that, as a dot over a squared plus 2a double dot over a. And if you combine that with the first Friedmann equation, and that's what you get. You get the a dot over a double dot over a, minus 4 pi g, and the energy density plus 3 times the pressure. This is called the second Friedmann equation. And if you look at this Friedmann equation, it actually relates the acceleration of the universe, the double time derivative of the scale factor. The first time derivative is like the expansion rate. The second time derivative is like the acceleration. The acceleration has this minus sign here. And in principle, you would think that the universe is decelerating show why of the sign here is negative. So the acceleration should be decreasing with time. So let's think about the possibility of having different types of fluids in the universe. So we'll see how different fluids will evolve in the universe. And one exercise I want you to try to do is the following. If you take a time derivative of the first Friedmann equation, you can derive what is called the continuity equation for this. It's like, this is like a matter conservation, if you want. And this continuity equation is just the time derivative of the energy density of the fluid plus 3 times the expansion rate of the universe times the energy density plus pressure equals 0. This is very easy to derive. I really recommend you to try to do it. This also follows from a more intuitive way by using conservation of energy momentum tensor and the first law of thermodynamics. So we can also see these things coming by writing the first law of thermodynamics as the variation of the internal energy of a system being equals to minus the pressure times the variation in the volume. And if you write the total energy as the energy density times the volume, and use the fact that the volume goes like the scale factor to the -3. Remember, the volume is like a distance cubed, but distances are decreasing as 1/a as the scale factor. Sorry, they're increasing as as a. Sorry, so the volume goes like 1 over. Sorry, the volume goes like. I'm sorry, the volume goes like a length to the cube, and then this goes like a to the. I think this is wrong. This may be a cubed. I'm sorry. And if you plug this, into this equation, you get the same thing as this. So I think this is sorry. This is a typo. I correct that. Now, if you want to study the evolution of the fluids, how the density, for instance, changes in the universe as time goes by, we have to solve this equation. In order to solve this equation, we have to know a relation between the pressure and the energy density. And this relation between pressure and energy density is what we call an equation of state. And this was alluded to already yesterday in the questions. So, so we need to postulate or find a relation between density and pressure, and that's what's called an equation of state. So the equation of state parameter is just this parameter W here. And we assume that there's a simple relation between the pressure of the fluid P and the energy density rho of this fluid. So I give you some examples. If you have matter that is described by Newtonian physics, so non-relativistic matter, it so happens that the pressure in this matter, we even call it dust, is very, very small compared to the energy density. So in this case, when you have non-relativistic matter, the equation of state is very well approximated by 0. It's pressureless matter. So we actually approximate all non-relativistic matter in the universe. No, be it atoms or dark matter, if it's non-relativistic, we approximate that as being as a fluid with pressure 0, which means the equation of state W equals 0. Now, if you have relativistic matter, so radiation, you may remember from your course in statistical mechanics when you treat a gas of relativistic particles that in that case, the pressure of a relativistic gas is 1/3 of its energy density. So for relativistic matter, radiation, photons, or any particle that is relativistic, the equation of state is 1/3. So W equals 1/3 if you're talking about, say, photons in the universe, okay? So those are the two cases that we know and we are used to. Now, there is another more non-intuitive case, which I'm going to describe now. So when we talked about the cosmological constant in the first lecture, I put the cosmological constant on the left-hand side of Einstein's equation, but you can also put on the right-hand side of Einstein's equation and interpret the cosmological constant as a component, as an energy momentum tensor. Component is a fluid that has an energy momentum tensor. And I left as an exercise also yesterday to show that the energy momentum tensor that corresponds to the cosmological constant is, I think maybe I wrote it here, is this energy momentum tensor. And you can write, so this, if you write this in terms of the energy momentum tensor of a perfect fluid, so this is the energy momentum tensor of cosmological constant, this is the energy momentum tensor of a perfect fluid. You see that comparing component by component, you see that in the case of cosmological constant, the rho, the energy density, equals to minus p, because these components are all the same. So what does that mean? That means that the equation of state for a cosmological constant is -1. So W equals -1 of the equation of state corresponds to a cosmological constant. Okay, so that's a result that we're going to use in these lectures a lot. So just to recap, the cosmological constant can be modeled as a perfect fluid with an equation of state W equals -1. Now, another exercise that's very easy to do is from the continuity equation, you can show, and using the equation of state, this general equation of state that the pressure equals W, this equation of state, W times the energy density. So just plug this in here and solve this equation. You can show, then you can solve the equation and show how the energy density changes with the scale factor. And you can easily show that the energy density changes as follows. It changes as a factor of A, of the scale factor, to the power -3, 1 plus W. So this is very easy to understand. Well, not easy to understand, but easily derive that, and I'll show you what that means for some of these fluids we just talked about, okay? And one observation I want to make is that I also solve this equation here. You assume that the equation of state is non-constant, it varies with time. So if you assume that W here, the equation of state, is not a constant but changes with time, you can also solve this equation. You just get in the exponent here an integral, and that's you can try this exercise. So, because some fluids, as we'll see also, are characterized by an equation of state that can change with time. Okay, so with this in hand, you can just show that a few cases of how the energy density changes with time. So suppose, just recall this equation. Suppose we're talking about non-relativistic matter. Non-relativistic matter, the equation of state is 0. So the energy density goes like A to the -3, just because there's -3 here and this is 0. So what does that mean? It means that if you have a volume in the universe with some non-relativistic matter in this volume, and the universe is expanding, the energy density, since matter is conserved, energy density will just decrease as the volume. So it will decrease as A to the -3. Now, what inverse of the volume? Increase the volume, you decrease the energy density as 1 over the volume. And 1 over the volume has this factor of A, the scale factor, to the -3. So this is completely expected. This is exactly what you think it happens if you have a box full of marbles, for instance. And you expand the box, and the energy density, of course, decreases with the size of the box. Now, if you have relativistic matter, like radiation, again, radiation is 1/3 here, right? The equation of state for relativistic matter is W equals 1/3. So this is 1/3 plus 1, this is 4/3, and then there's this factor 3, so it goes like a to the minus 4. So the energy density in radiation drops faster than matter. And the reason being that the energy in each photon is also changing with the expansion of the universe. And think of the energy of the photon being associated with its wavelength, as you know. So if the wavelength increases, the energy of the photon decreases. So this gives you an extra scale factor dependence here. And this is why the energy density in radiation, it falls faster than matter. Okay. And now the strange thing is what happens when you have only cosmological constant, right? If a fluid is a cosmological constant, the equation of state I just mentioned that the equation of state for a cosmological constant equals -1, so -1 plus 1 equals 0, and the result is that for a cosmological constant, the energy density is constant, does not change with time. Okay. This just follows from these very simple considerations here of solving the continuity equation, this equation with given equation of state. Okay, and with this information, I can draw my favorite figure, my favorite plot of the universe, and this is it. So this is a plot of the logarithm of the density function of the logarithm of the scale factor, and so time is going this way from left to right. So the scale factor today, if you remember my definition and everybody's definition, is that the scale factor today is 1, which means that the logarithm is 0. So when I put 0 here, it means today, and here you go to the past, right? So matter goes like a to the minus 3. Radiation falls faster. That's what we saw. Goes like a to the minus 4. So it's in a log-log plot. Those are straight lines. And the cosmological constant does not change at all. Okay. So this plot tells you a lot about our universe. First of all, if you're here today, I think I showed in the first pi chart that I put in yesterday that the contribution of radiation today is completely negligible. And today we're actually dominated by cosmological constant, right? So this is the picture we have today. But if you go back in time, things change radically. Back in time, first of all, the cosmological constant becomes irrelevant because its energy density remains constant. And what really dominates at early times is radiation. So basically, electromagnetic radiation. So when you go back in time, radiation dominates. So the universe is very hot, and the energy density increases a lot. And this is the reason why our whole universe was in a hot, dense state, very far in the back. So the guys from the Big Bang Theory, they were correct. And also from this plot, you can see some interesting eras in the universe. So there's an era where the universe is dominated by radiation, and that happens before this equality time here, when the densities are the same. And also there is an equality time when the density of the cosmological constant is equal to the density of matter. And that's when the cosmological constant starts to dominate the universe, and when the acceleration, accelerated expansion of the universe actually starts. So back here, again, cosmological constant is irrelevant, and the universe is expanding as it should, decelerating. And this, as we will see, has consequences because we need to form galaxies. And galaxies only form when the universe is decelerating. And in recent times, the universe started to accelerate. So I see there are a few questions, so maybe it's a good time to pause and ask for questions.
So the first question is if there are probes to check this figure that you are just showing now.
Of course, yes. We have lots of probes. CMB is one of the probes, so we will talk about the probes.
So you will talk more about it later. Okay.
Oh yeah, sure.
There's a question which I'm not sure I understand. Says something special in the phenomenological sense happens during matter domination. I'm not sure what is exactly pointing out. Martin, if you can elaborate on that. In the meanwhile, the last question was, if the energy density keeps constant and the universe is expanding, it seems that there is energy being created from nowhere. What happens to the energy conservation of the energy?
Right. So the cosmological constant, you can think of, energy conservation in the universe, first of all, is a tricky business, because energy conservation in general relativity is a tricky business. Energy is not even a scalar, Lorentz is scalar. So energy conservation is a bit tricky. But all I want to say about this is that I have a picture later on that for the cosmological constant, for instance, we can think of it as a vacuum energy. So if you increase the size of the universe, there will be more space and therefore more energy density in the form of a cosmological constant, because that's the characteristic of a cosmological constant. So its energy density is energy is proportional to space. Its energy density is a constant, so the total amount of energy is proportional to the volume that we're talking about. So so the expansion of the universe you can think of being is energetically favorable for the universe to expand, if you want. Okay, can I continue, Ron?
Yeah, 1 second. There are a couple of more questions. So in this plot, the content of matter is just baryonic matter or includes also dark matter?
Yeah. So first of all, this is a very, very qualitative plot. It's not quantitative at all. It's probably not in scale. But the answer to the question is any non-relativistic matter behaves like this. Okay. So in order to know, actually, there will be an exercise that give it to you that you have to compute when the equality here happens, when this thing happens. So you'll be able to compute those things. It will all depend on measurable quantities today. All right?
All right. And finally, there is one more question that says, why we need a decelerating universe to form a galaxy?
No, it's the opposite. If the universe is accelerating, you cannot form galaxies. So that's why, in fact, I mentioned this later. Actually, you see that why is that later. But intuitively, you need the gravity to be dominating in order to form bound states, galaxies, for instance. Right? If the cosmological constant is dominating, there is no way to form bound states, and you will not form galaxies. You suppress galactic formation. So if the universe was always accelerating, was always dominated by the cosmological constant, we will not be here. And in fact, this argument, we will not be here. This is called the Entropic Argument. If I don't know if you guys are familiar. I talk a little bit more about the Entropic Argument. But Entropic Argument is the following: if something had happened and it would cause life to be non-existent, so this thing did not happen. So this is called entropic argument in very simple terms. Now, yeah, but then of course there are things in this plot that you have to think about. For instance, the cosmological constant. Why is this cosmological constant starting to dominate recently? This line here could be, if the line was up here, then we would not have galaxies, for instance. Okay? But the line could be zero. There's no reason why we don't see any reasons why there should be a cosmological constant. So this is an experimental fact. And also, value of the cosmological constant is a problem. We don't know how to estimate, and I'll talk about a little bit more about this. The value of the cosmological constant. So this is called the cosmological constant problem, by the way. So we don't know why the cosmological constant starts to dominate right now. It's called coincidence problem, and it has to do with the with the size of the cosmological constant. It's measured, by the way. So these are interesting questions that we have to keep in mind, okay, in this very simple model with a cosmological constant. And also notice that in the future of the universe, if the model is correct, there's no escape from acceleration. Okay? So the universe will keep accelerating in the future.
Okay, there is one more question that says, can we think there was a phase shift during the shift from radiation dominant to matter dominant? Can we think of it as some symmetry breaking of some background symmetry?
So the question is if there's a transition from matter domination from radiation domination to matter domination, there's some symmetry breaking the background. Is this the question?
It seems to be the question, yeah.
Yeah, no. This is it's something very simple. Just the way the average universe is expanding. There is no breaking of anything. It's just the dynamic evolution of the universe. There's no symmetry associated with those.
Okay. There are no more questions, so I think you can go ahead.
Okay, thank you. So now we can also see how the scale factor changes with time, for instance, okay? And this is something interesting to know. And in fact, if you remember the first Friedman's equation, let me put back here. This is the first Friedman equation. So it says that the expansion rate square goes like the density. So the expansion rate goes like the square root of the density. So this is what I wrote here. Expansion rate goes like the square root of the density. And we just showed that the density goes like the scale factor to -3, 1 plus the equation of state. So it's very simple exercise to plug this in here and show that the scale factor as a function of time goes like the time to the power 2 over 3, 1 plus w. Okay? Just show that. It's very simple to do. So which means that the expansion of the universe changes with time. The expansion rate of the universe changes with time. The expansion of the universe changes with time when you change from a regime of matter to radiation dominated. I think okay. All right. So you can show that, for instance, matter, when the universe is matter dominated, remember, matter domination means W equals 0. W equals 0 means that the expansion rate goes as t to the 2/3. And if the universe is radiation dominated, remember, the radiation means W equals 1/3. So 1/3 plus 1 is 4/3, and then this goes like t to 1/2. So this is how the scale factor changes with time as you change from matter domination to radiation. Now there's something funny. What happens now in the case of the universe dominated by a cosmological constant? I just mentioned to you that when the universe is dominated by a cosmological constant, the cosmological constant has the property that its energy density is a constant, which means that A dot over A is a constant, which we can call H. So the Hubble parameter is a constant in this case. And you can solve this equation easily. You show that the scale factor, in this case, where you have a cosmological constant that is dominating the universe, actually grows exponentially. So it just follows from this very simple consideration. So you have an exponential growth of the universe when the universe is dominated by cosmological constant, for instance. So, so the exponential growth means that the universe is accelerating. In fact, if you look again at the second Friedman equation that I just showed to you, and you can derive easily, and you put the equation of state that W equals -1. So here, 3 times P equals -3 times rho. You see that the acceleration is positive. It goes like rho, right? So it just means that the universe is, in fact, accelerating when it's dominated by dark energy or cosmological constant in this case. So when I say dark energy, I will mean something that is responsible for the acceleration of the universe. And the simplest model for dark energy is a cosmological constant, okay? So what we know now is that the universe started to accelerate a couple of billion years ago. And before that, there was a period of normal decelerated expansion, which, as I mentioned before, it was essential for the formation of galaxies. This is a cartoon showing that you start the universe around, we call Big Bang, but it's not really an explosion. And in fact, we believe in the very beginning, very early terms of the universe, there was another phase of accelerated expansion, which we call inflation, and that solves several problems of the standard model of cosmology. And then the universe starts to decelerate after inflation. So this is time, sorry, and this is kind of the size of the universe. And then at some point around here, after galaxies were formed, the universe starts to accelerate again. That's that's our picture that we have of the universe right now. In fact, we can see supernovas that are far away to being a period where the universe was not accelerating. That's very interesting. I just want to mention a curiosity here. So, we can characterize these fluids by the equation of state, at least at this level of average fluid. And, you may wonder, I gave you an example where this equation of state was 0, that's dust or non-relativistic matter, 1/3 relativistic matter, and -1 if it's the cosmological constant. You may wonder if it's possible that, or not if it's possible, but what would happen if the equation of state were smaller than -1? And this is goes in the literature by the name of phantom dark energy. And there are strange things that can happen in phantom dark energy. So the universe is expanding very, very fast. And in fact, it can show that density increases with time. And that there's a singularity at a finite time. So singularity means the scale factor diverges at finite time. And this is called a big rip singularity. And that actually was a physical review letters back in 2003. And that's just fun to, it's just, with the same tools that you just learned, you can explore what happens when the equation of state is smaller than -1. Now, if you ask me if I know any model where the equation of state is smaller than -1, I have to say that I don't know any natural model where that happens. Okay, now we can talk about how to make our universe, a recipe for our universe. So first of all, I have to say that there is a critical density at which the universe is spatially flat. So I just assumed that there was no curvature to begin with, so I spatial curvature. So in the beginning of the lecture, when I wrote, yesterday actually, when I wrote the metric for Freeman, Robertson, Walker, I explicitly mentioned that I would not include the possibility of curvature, spatial curvature, and I would assume the universe was spatially flat. And that happens when the universe has a critical density today. This is the critical density it should have today. Does this look familiar to you, this equation? This is just Friedman's equation again today, right? So Friedman, remember that Friedman's equation was h squared equals 8 pi g over 3. So this is just Friedman's equation. And that the way to write Friedman's equation in that fashion assumed that the universe was spatially flat. So today, the universe has to have this critical density. And this is something, actually, yeah. There's an exercise for you here, exercise 6, I want you to do. I want you to use data on the Hubble constant. So assume, for instance, the Hubble constant is between, assume the Hubble constant is 70 kilometers per second per megaparsec, and compute what is the critical density of the universe, okay, today. And I want to do it in units of number of protons per cubic meter. This is an energy density, so you can have units of energy to the -4, whatever you want. But I want, sorry, energy to the 4th. But I want it to compute as in these units, so protons per cubic meter. You know, what would be, this would give an idea of the average density today of the universe, because we know that from measurements, which I didn't talk yet, but we know that the curvature is 0 or very close to 0. So we know that we are at the critical density. So in this way, it will give an idea of what is the average density of the universe in units of protons per cubic meter. And this number is interesting to know. So I want you to try to estimate this critical density, just the order of magnitude, okay? Just for you to have a number in the back of your mind when you talk about critical density and what is the average density of the universe. Now, yes?
There's a question.
Yes?
Just a second. It's a question from Alison Silva. Alison, go ahead. You can ask it yourself.
Hi.
Hello?
Can you hear me, Rogerio?
Yes.
Hi. All right. So in the early universe, you should have a very hot quark-gluon plasma, right? So why don't we consider an energy momentum tensor for something like that? You know, a fluid, nonlinear, possible with vorticity. Why don't we do this? Why do we stick with the idea of perfect fluid?
Right. So yes, you're right. So we have in the early universe, we have you know, so you don't have protons anymore. When you go to higher temperatures, the protons dissolve and we have quarks and gluons, and they form a quark-gluon plasma. But if you go to very large temperatures, you know, QCD is asymptotically free. So and that's why the couplings are small. And you can, in principle, you can assume that you have a fluid of quarks and gluons separately if the coupling is very small, which happens at very large energies because of asymptotic freedom. So alpha QCD is small at very large energies or large temperatures in this case. So of course, when you are close to the temperature where the interactions become strong and you have phase transition, then this description will break down. So
right,
during phase transition,
in the energy momentum tensor itself, right? But in the energy momentum tensor itself, can't we consider, you know, a plasma or something? Tensor for a
yeah,
would that make
you can,
sense?
you can. But again, to a first approximation, you can think of quarks and gluons at very large energies as being free, just because the coupling constant is very small. If they're strongly coupled,
right,
yes, then you have to change things. But as long as you're considering temperatures very much larger than the temperature of the QCD phase, so we call this the QCD phase transition, confinement phase transition, when you evolve from a free soup of gluons and quarks to a to hadrons, for instance, right? Then things are much more complicated. But so,
right,
but
thanks.
this happens at a very small interval in time. So if you are very large energies, so the approximation is this. If you are at a very large energies, you can consider the universe as being made of quarks and gluons, free quarks and gluons. And if you're below the energy of confinement, then the description changes. Then you have a gas of ions, kaons, protons, neutrons, etc.
I see.
Does that make sense?
Just for the early period, we can consider this.
Yeah. So,
All right,
so
thanks.
what I want to say is that only for a short period of time, you have to be concerned about this transition of quarks and gluons, free quarks and gluons, to hadrons. And that's a phase transition. That's a big event in the universe. It's a phase transition called the confinement phase transition, or the phase transition.
All right, thanks.
Okay, you're welcome. Any other questions?
No, there are no
John?
further questions. No.
Okay. So yeah, so this exercise, I really want you to try to estimate this critical density, and you'll be surprised to know what is the average density of the universe in units of protons per cubic. Now, yeah, so for that, just assume it's just order of magnitude. So just assume that the Hubble constant is 70 kilometers per second per megaparsec. So I put here some values of the Hubble constant that are measured today. And you should notice that there's a mild tension. It's becoming more important about two types of measurements of the Hubble constant. One is using the supernova type 1a that I mentioned briefly using the Hubble Space Telescope. And the other measurement is an indirect measurement using the CMB, microwave background, from the Planck satellite. And this is a plot, recent plot of these measurements. And there's a discrepancy which comes from measurements of what's called early measurements, early times, CMB, BAO, for instance, baryon acoustic oscillations, big bang nucleosynthesis, and late time, which is basically supernovas and other methods. And I want to call your attention that there may be a 5 sigma-ish discrepancy in the Hubble parameter as measured by these two different methods. Okay, and I'll talk more about this later because this may be a sign, maybe one of the first signs that the lambda CDM model has some problems. This is very exciting, and you should keep an eye on this. And I will discuss a little bit more about this later. Okay, now coming back to our average universe, so we can characterize the universe or the recipe of the universe in terms of the different contributions to the energy density budget of the universe. So remember that I defined the rho critical here, the density of the universe today, which is called density rho critical. And one can define these quantities, which are nice and dimensionless, this capital omega I, for each ingredient of the universe. So each ingredient of the universe, each contribution, each ingredient of the universe gives you the contribution to the energy density budget, which we characterize by these parameters omega I, which is the density in this component I divided by the critical density. And of course, if we're especially flat universe, which means that if you sum all the energy densities of different components, it gives the critical density. So which means that if you sum all of these omega i's here, you should get 1. And again, this is a very nice quantity because you can rewrite the first Friedmann's equation. Remember, it was a dot over a squared. So this is h so the Hubble function squared divided by Hubble constant today. So you can rewrite using this quantities omega I. You can rewrite Friedmann's equation this very nice way. Okay, so the Hubble squared divided by Hubble constant squared equals the sum of the different components times the scale factor to the power -3, 1 plus Wi. So Wi is the equation of state for this component here. And this, again, assuming constant equation of state, which does not have to be the case, but for simplicity. This equation is also nicely written in terms of redshift instead of scale factor. So just substitute the scale factor by its definition in terms of redshift. So A, if you remember, the scale factor is 1 over 1 plus Z. So this equation here would give you, instead of A to the -3, 1 plus Wi, would give you 1 plus Z to plus 3, 1 plus Wi. Okay. So those are the equations that we usually solve in order to find how the universe is expanding on average. And that's when I want to give you an exercise just to practice. So suppose I give you a recipe of a universe. So a universe which today has 70% of dark energy in the form of a cosmological constant, 30% of non-relativistic matter, and very small quantity of radiation. Okay, so these are the things I wanted to compute. I want to compute the Hubble, assume Hubble as being 70 kilometers per second per megaparsec, the Hubble constant. And this is just an exercise in units. You can write this, the inverse of the Hubble constant in units of years. And that's actually what sets the age of the universe. Then you can compute the age of the universe for this type of universe. It's not going to be much different from this. I wanted to compute the 1/4 power of the critical density, because this has units of energy. Remember, energy rho is energy density, has units of energy to the 4th power. And if you take the 4th root, you get units of energy. And this is the scale of the energy that's associated with the cosmological constant. Nice exercise where you see what is the energy scale that is actually associated with the cosmological constant. And another thing, another exercise in units is the Hubble constant in units of electron volts. And you see that is much, much, much smaller than this. And then also with this recipe of the universe, you can compute at what redshift matter and radiation have the same quantity. So this is the equality of matter and radiation. And also I wanted to estimate the redshift at which the cosmological constant energy density equals to the matter energy density. So this gives you things that happens in this plot here that I showed. This is when dark energy starts to dominate, and this is the equality between matter and radiation. All in this exercise. I hope you try to it's not very difficult. Okay. So it's a good time to pause for more questions, Juan, if there are any.
There are no questions.
So let's continue. So some people, including me, we're not very happy with the cosmological constant as a model for dark energy. And I'll talk a little bit more about that later. But people have come up with the idea of a possibility, at least, to have a more dynamical model for dark energy. And the idea being that maybe, don't know much about dark energy, but maybe dark energy is the energy stored in a scalar field, for instance. So that's the basic idea behind some dynamical dark energy models. This sometimes, when you have a scalar field that can be responsible for dark energy, sometimes this goes under the name of quintessence, quintessence fields. So for a real homogeneous scalar field, the energy momentum tensor is one of the exercises I gave you yesterday. is given by for a scalar field, a homogeneous scalar field, the energy density is just 1/2 of phi dot square, with the scalar field denoted by phi, plus the potential energy. So for a very simple Lagrangian, canonical normalized scalar field Lagrangian, you derived what energy momentum tensor is, and you can compute for a homogeneous field what is the energy density. The energy density is 1/2 of phi dot square plus the potential energy field phi, and the II component of the energy momentum tensor for a scalar field is just given by 1/2 of phi dot square minus V of phi. Therefore, for a scalar field, homogeneous scalar field, we can compute immediately what is the equation of state, because the equation of state is just the ratio of pressure over the energy density. And we just saw that this ratio is 1/2 of phi dot square minus V of phi and 1/2 phi dot square plus V of phi. Now this thing changes with time, okay? But you can see from this expression what are the maximum and the minimum values that the equation of state for a canonically normalized scalar field can have. So suppose you are in a situation where you can think of phi dot square as being the kinetic energy and V of phi as being the potential energy. So you can be in a situation where the kinetic energy of the scalar field, so the scalar field is moving, it's rolling down potential, for instance, say the kinetic energy is much larger than the potential energy. So if that's the case, the equation of state is 1, right? Or you can be in the opposite situation, where the potential energy is completely dominant over the kinetic energies. Let's say a situation where the scalar field is moving very slowly, and that's the situation where the equation of state is close to -1. So in this case, the scalar field equation of state can be anywhere between -1 and 1. Okay. In particular, these models I mentioned just a curiosity a couple minutes before, these models of phantom dark energy cannot be realized in simple canonically normalized scalar fields. Now, I suppose you're in a situation where the potential energy dominates. Potential energy dominates in a situation where the equation of state is close to -1. And in fact, the scalar field resembles a cosmological constant. And in that case, it would qualify as being a quintessence field. I just mentioned this name, just a name. Quintessence field is a scalar field that can be responsible for the dark energy, the accelerated expansion of the universe. Now, these fields, there are some problems with these models, of course. They have to be ultralight in order to not to roll down to bottom of the potential state there. Anyways, there are some issues also about these models, but I just want to mention that one possibility to go beyond simple cosmological constant is to invoke a new field which is responsible for the recent acceleration of the universe. Of course, the same thing can happen in the early stages of the universe, and this field will be responsible for inflation. What happens at the early stages of the universe, same type of physics, and I will discuss much more about inflation later on during the week.
Rogerio, there are various questions.
Yes.
So, first is, what do you mean with ultralight?
Ultralight, sorry, I wasn't here. So in this exercise, I wanted you to compute the value of the Hubble constant, units of electron volts. So the Hubble constant has units of energy, right, or mass. And here I say ultralight, I mean a field that has a mass of the order of the Hubble scale. So I have to compute this, and you see what I mean by ultralight. So
Okay.
it's part of the exercise. You have to tell me what ultralight is. You see that's really, really light.
Then there's a question that says, why does pressure have that expression?
Why what? Sorry?
Why does pressure have this expression?
Ah, good. So
That's the
this also, in the, yesterday, I told you how to compute the energy momentum tensor for a scalar field, right? And so if you go back to this lecture, yesterday lecture, there's an expression for this component here, which is given by this. This is not in the lecture, but this is on the right by a simple computation. Again, using a homogeneous. It's not difficult to include fields that are not homogeneous. There's a Laplacian. But this is in that lecture yesterday, and you can go through it. There's an expression for the energy momentum tensor of the scalar field, and if you take the II component for a homogeneous scalar field, that's what you will get.
Okay. Another question. So there are 2 or 3 more. The next question is, how is the potential?
How is the potential?
I'm not sure I understand the question, but I guess he's asking if what's the function for this potential.
Right. So it's up to you to decide. So I have to choose a potential. For inflation, we are going to see different types of potentials, and for dark energy, there are different types of potentials too. So usually, what you want a potential in which the scalar field is moving but not moving too fast. So it could be, for instance, the simplest thing is a quadratic potential. So m square phi square, and in that case, the mass has to be super, super small in order for the field not to roll too fast to the minimum of the potential and stay there. So yeah, so this is part of model building for type of models. There are many potentials that were discussed in the literature for quintessence, and there are some potentials that have very interesting properties. Points when you solve the equations of motion. So there are many interesting properties that you can obtain from given potentials.
Okay, there's a follow-up by Christian who asked about the potential, who asks, can the scalar field describe all the components of the universe? Matter, radiation, dark energy?
Right. So we know that matter. We know what baryons are, quarks and photons. That we know what they are, right? So maybe for dark energy, yes. So there are models. I don't think there's any model that's totally satisfactory, but there are models where dark energy is a scalar field. There are models where dark energy is a different vector field. Models. Now now you're referring to the only other component is dark matter. Dark matter we have no clue. Dark matter, it can be a scalar field. But most models of dark matter, and I'll talk about dark matter also later on, but there'll be lectures on dark matter next week. Most models of dark matter that are motivated by, for instance, particle physics, supersymmetry especially, dark matter is not a scalar field, is a Fermi. Okay, but I have worked in models where dark matter is a scalar field. I think I even show a couple of slides about that. So the answer is yes, dark matter can be a scalar field. And dark energy too can be a scalar field.
But not the whole matter, as we are seeing in the lecture of Andrea. So
no, we have less,
sure.
No? we are not scalar fields.
Right.
I hope that's clear.
He was asking all the matter. I don't know what he was referring exactly.
Yes. We are not made of scalar fields, and up to now, just to make it clear, there's only one scalar field we know of in nature. Okay? Fundamental, as far as we know, And that's the Higgs field.
Right.
That's unstable. Certainly cannot be dark matter.
Okay, so Samantha Saha is asking, could you explain what's the motivation of taking the homogeneous scalar field?
Right. So we are talking about, again, the average expansion of the universe. So in the average expansion of the universe, we describe the universe as being homogeneous and isotropic. So if I want the scalar field to describe dark energy, which is homogeneous and isotropic, the scalar field must be also homogeneous and isotropic. Hence, it cannot depend on the position of space-time that I'm picking. It can depend only on time, but not on the position. I hope that's clear, someone. Of course, when you consider perturbations, then you have to consider all sorts of non-homogeneous scalar. Here, we're still talking about an average universe, okay?
Right. So there are inhomogeneities, but they are much smaller than the
Yeah, exactly. So we'll talk about inhomogeneities later, but for the moment, we're just looking how the universe would evolve if it were homogeneous and isotropic.
So Samantha is saying, she has a follow-up, and she says, I was asking why scalar field? So what do you mean? As opposite to what? I would say. So the question is, why a scalar field? That's the question. But I'm not sure what she has in mind. She's asking, it could be a fermion or a vector. She's asking.
Right. So we think of this as being, again, this is a classical description, not quantum yet. So it's it's related to the fact that, as Andrea was explaining, why a fermion cannot have a vacuum expectation value, cannot have a classical description, if you will. The vector would obviously break also Lorentz invariant. So the scalar field does not break any symmetries. This classical scalar field does not break any of the symmetries of the universe. So that's why we work with this.
Right. So then there's the last question for the moment by Jefferson Sales is how one can evaluate which values of the scalar field are allowed in order to have formation of structures and later on a dark energy epoch.
Can you repeat?
Yes. How one can evaluate which values of the scalar field are allowed in order to have formation of structures and later on a dark energy epoch?
Very good. So the idea is that the energy density of the scalar field is changing with time. So at early epochs, the energy density should be small compared to matter radiation, so that the universe would be its usual decelerating expansion phase. But today, the energy density would be dominant of the scalar field. So in order to see what values of the scalar field specifically, what you have to do is to solve the equations of motion for the scalar field with some initial conditions. And then you can solve these equations of motion and see exactly how the energy density changes with time. Again, that depends on initial. Now, I think I have in a few more slides, what is the equation of the scalar field that you have to solve? You're probably familiar with the Klein-Gordon equation. And in an expanding universe, the Klein-Gordon equation for a scalar field has to be modified. And I'll show you how.
Good. There is one last question by Christian Calderon. He's asking, are there models where the scalar field is complex?
Yes, there are. Now, when a scalar field is complex, that's interesting. Then you have 2 degrees of freedom, right? And so you can, as Andrea was doing for me. He was writing, you can write a scalar field as with two real functions, phi1 plus I phi2, or you can write as a rho e to the I phi, for instance. And you have to be careful with what these two components are doing. And I think it's very amusing that it's possible to write models where one of the components of the complex scalar field can be responsible for inflation, and the other component of the scalar field can be responsible for energy. So in fact, I wrote a model many years ago with this possibility with Josh Freeman. So this was called a simple model of quintessential inflation. Anyway, so yes, it's fine.
Okay, cool. So there are no more questions. I think you can go ahead, or yeah.
Okay.
It's
So
5:12. I mean,
how many minutes I have?
So I think officially you have 3 minutes.
Okay.
But of course you can take some more if you need it.
No, I finished in 3 minutes. I just want to show you, since you are curious about different models for dark energy, and this is a page with some of the models that people have thought about. So this is the simple cosmological constant. This is the canonical scalar field, which is sometimes called quintessence field. And this is not some model. This is just a perfect fluid with some perturbation. This is something that people have talked about in the past, but I think this model has basically been ruled out. It's called the Chaplygin gas with equation of state. It's even wrong. It should be P here or here. K-essence models where you have a generalizations of these scalar field, tachyon fields, Born-Infeld Lagrangians. So there are a whole set of models that were considered as possible dark energy models. So this is a very active area people are working on. So okay, this is what I wanted to show you. You can derive this also from the lectures. But I want to derive for you the Klein-Gordon equation. So there was a question of how scalar fields evolve, and they're classical fields. They obey the Klein-Gordon equation. But when you have an expanding space, non-Minkowski space-time, the Klein-Gordon equation is changed, and this is how it is changed. So you have a very simple Lagrangian, the canonical normalized scalar field. So the kinetic term minus the potential term. So you write the action. You find the equations of motion like you do for the regular action in flat space-time. And what you find is that the equation of motion has this form here because you have to consider. Sorry, there's a typo here. There should be a square root of minus g in this action. I'm very sorry. We'll correct that. So when you do this variation here, you know this trick of partial derivatives that you write in terms of a total derivative, etc. What you pick up is a factor of derivatives of the square root of minus g. So just to remind you, if you are in Minkowski space, square root of minus g is the determinant of the matrix. So in flat Minkowski space, this is a 1, and you have box phi plus dv phi equals 0, which is the usual equation of motion. Now, if you are in Freeman-Robson-Walker, for instance, the determinant is a6 of t, so the square root of the determinant is a cube. And again, for a homogeneous scalar field, you can go and derive this equation here for the motion of the scalar field. So if you want to find how the scalar field changes with time in an expanding universe, in Freeman-Robson-Walker expanding universe, that's the equation you have to solve for the scalar field with some initial condition. So this equation is valid for any scalar field, homogeneous scalar field in our expanding universe. Okay, so it's 12:15. I think I will stop here for more questions.
There are no more questions for the moment.
When I'm going to talk about initial conditions, that's
Okay.
never going to talk about initial conditions.
Well, there were various questions already, so maybe they will have more when we come back for the questions and answer session. Oh, no, wait, there are some now. No. There are questions about the link of the slides. Okay. Okay, Christian has a question. Are there ways to test the different dark matter energy models?
Sure, that's what we do, right? So, for instance, so different dark energy models, right? That's what you said. Yeah. Dark energy models. Again, you have to tell me what is a different model from lambda CDM. So a different model from lambda CDM, it can be something very, very simple. For instance, suppose I have a model where the equation of state is not -1, because what characterizes lambda CDM is equation of state W equals -1. Now, suppose you have a model where W is not equals to -1, but let's check if just having a constant equation of state different from -1 can help to explain some of the observables of the universe. And we did that in the dark energy survey. We allowed for a equation of state different from -1, and then we looked at our data and we fitted for the equation of state, which was let to be a free parameter in our fit. And that's what the value was.
Good. There are some more questions. What do you think, Rogerio? We should go through them, or I keep them and then we raise them again during the question and answer?
I think we can keep them for the question and answer, no?
Okay. So
Is that
I'll
okay?
save there are 3 questions which I see now. I will save those and remind them later in the Q&A. Yeah, we did the same with Andrea, so it should be fine.
Yeah, I just want to answer this Ankit and evolve, because it says W is one of the lambda CDM parameters that's fitted to data. That's not correct. Lambda CDM by definition has W equals -1. So it's not lambda CDM, it's another model which is called WCDM.
Right.
Okay.
Okay, so I'll save the questions that are written now, and we can start later with those. Okay.
Right. So Joan, you are Enrico is the host. Okay.
Yes, I'm still the host. So I will have a meeting in a while, and I will miss the first part of the question and answers. But I will stay online.